Hey, Science 30. So this last video here is going to be on magnetic fields for our physics topics. And so magnetic fields, uh, we've got two poles in magnetic theory, north and south. And so this makes magnets what we call dipolar. Di being two, polar means poles. So we've got two poles on a magnet. Attraction and repulsion occurs just as with electrical fields. So north and north, you're going to get repulsion. South and south, you're going to get repulsion. North to south, you're going to get attraction. Which magnets will attract and which will repel? Well, label your pictures so we just did that together. Some elements have stronger magnetic properties than others. So there's certain kind of magnets that get grouped together. There's fancy names. Groups 8, 9, and 10 make stronger magnets, and they're what we call ferromagnetic. So they contain certain metals like iron, nickel, or cobalt, which make them quite a bit more magnetically charged. So ferromagnetic materials, each magnet is made up of tiny magnetic domains. So instead of having just a random magnet, like a weaker fridge magnet, doesn't get a really good stick, right? When you get a really strong magnet, you know it's got a strong magnet because it's quite magnetic, and that's because all of the alignment of the magnetic domains are all proper and straight. Weak magnets have a random arrangement of magnetic domains, so they just don't stick as well. So weak magnets can become stronger by exposing them to an external magnetic field. So you can actually rearrange the magnetic domains and make a weak magnet stronger, but fridge magnet's never going to get that opportunity. So magnetic field strength and lines, similar graph to what we've been doing, but if I just quickly graph this here, the further away you get from a magnetically charged object, the less the magnetic field strength is going to be. Makes sense, right? I could put a magnet next to something sticky or magnetic, it'll stick right away. If I pull it away, it's going to not go back towards the fridge and get stuck, because the further away I get from the magnetic surface, I reduce the magnetic field strength. So magnetic field lines, to determine the direction of magnetic field lines, we use a north test body and see which direction it will move. And so magnetic fields always move out of the north and into the south. Much like we always go from positive to negative in electrical fields, or from small objects to big objects in gravitational fields, in magnetic fields we're always moving out of the north into the south, out of the north into the south. So out of the north into the south. So Earth's a little wonky. Now this is gonna might trip you up a little bit. So why does a compass always point north? Well, the compass is always attracting towards Earth's magnetic field. Now, geographical north is classic top of the Earth, next to the Arctic. The geographical south pole is way down at the bottom of the Earth. But according to our field lines, it's actually the opposite. Magnetic south is actually at the top of the Earth, and the magnetic north is actually at the bottom of the Earth. So our geographical north pole is actually the magnetic south pole, and the geographical south pole is actually the magnetic north pole, which is a little confusing. Northern and southern lights, this is kind of cool. So the northern lights, and if you're on the other side of the atmosphere, or hemisphere, it's southern lights. Charged particles from the sun are called solar winds, and they can sometimes hit the Earth's atmosphere. Solar winds get trapped within the magnetic field of the Earth, and they collide and they hit the air, and with all the gases in the atmosphere, they become electrically charged and start producing all these lights, which is kind of neat. So a magnetic field is generated in two ways, either through the movement of electrons around a nucleus and then the spinning of electrons on its axis, or by producing an electrical current by passing a coil of conducting wire through electricity through a coil. So if I can take electricity and pump it through a coil, I can create an electrical field, a magnetic field, or I can move electrons around a nucleus and spin, and it'll create an electrical field as well. Pardon me, a magnetic field. Here's a quick review of all three of our fields, so I'll let you pause it here and see if you can figure out the type of field based off the diagrams. Here's the answers. This first one here is an electrical field. A bar magnet is going to show a magnetic field. An asteroid is going to be a gravitational field. Stars, gravitational field. A plastic wrapper that has gained electrons is going to be an electric field. And the Earth is a gravitational. And of course, if we talk about magnetic north and magnetic south, it's also a magnetic field. Okay, guys, thanks very much. That's magnetic fields. There's no calculation that we're going to do for this one. So that's it. That's all for field theory. Thanks.